Okay, welcome to the 24th class meeting of EECE574, the graduate level probability and random processes. We are studying random processes, especially last time we defined a lot of classes of random processes. And these definitions were all motivated by the Kolmogov's extension theorem or existence theorem. And the Kolmogov's theorem is not only links the major theoretic definition based on sample path and ensemble of a random process with the familiar joint CDFs, but also they read us a lot of definitions, classifications of random processes. So last time we studied the class of random processes called stationary to order 1. So let's say this is the set of all random processes. And then we have an infinitesimally small subset, but let me exaggerate a lot. So here goes the stationary to order 1. Okay. What does that mean? Stationary to order 1 means that the distribution at any time instant. So you fix time, then what do you have given a random process? You have a random variable. So since the time index is a member of a countable set or an uncountable set when we talk about random processes, we have infinitely many random variables. And the first order stationarity means that these infinitely many random variables have the same distribution at any time. So this is time index, or that is time index. You have some t0 and 0. And then here you have x of t0, x of n0. Ready? So whatever t0 you choose as a random variable, this guy have fixed time invariant stationary CDF. Also, if capital X of n, a discrete random process, is stationary to order 1, then its sample at any time has the same distribution as a random variable. Got it? So that is the definition of stationarity to order 1. Then what is the consequence of this stationarity? Of course, the first order moment, second order moment, any nth order moment also stationary, right? And the ensemble average expected value of x of t becomes constant, either in continuous time case or discrete time case. Now you understand why some people prefer using this notation. Because we don't sometimes need to distinguish a discrete time random process or a continuous time random process. However, to our electrical engineers, this parenthesis means continuous time, and this square bracket means discrete time. So even some professors who wrote the textbook on random process prefer this notation because they can talk about discrete time, continuous time at the same time. So stationary to order 1 implies the mean path is constant function. However, the converse is not true. As I emphasized last time, there are many, many, many different probability distributions having the, for example, mean 0. Ready? Then we define the stationary random process to order 2. And in this case, what we do is that we sample at 2 time instants. So for example, here and there. Okay, let's say this is t1 and this is t2. And now we have 2 random variables because we sampled at 2 time instants. Then what is the full characterization? joint CDF, PDF, PMF. And this does not change as you translate these 2 points in time domain. So given fixed time difference, the joint PDF, CDF, PMF characteristic function does not change. However, if you change this time difference, then the distribution may change. Got it? What about stationary to order 3, 4, 5, any n? Now you sample at n time instance. Then you have random vector of length n. And that random vector's joint CDF, PDF, PMF characteristic function does not change as far as you add or subtract the same amount of time offset from the time instance. That means stationarity. Got it? Now, what are the relations between first stationary to order 1, order 2, order n? So we have smaller and smaller set. And eventually, we may say that a random process has time invariant joint PDF, CDF, PMF, or characteristic function for any number of samples, any finite number of samples. In that case, we call a random process is strictly stationary. And this is strict sense stationarity. And as I wrote here, drawn here, strict sense stationarity is most restrictive, and it is automatically stationary to order any finite number, 1, 2, something. Since these definitions are too strong and too restrictive, sometimes we just define a class of random processes in terms of the mean path and the autocorrelation function. What is the autocorrelation function? Since we sample at 2 time instance, the autocorrelation function is defined naturally as 2 variable function. It is denoted by R sub XX of T1 and T2, but I prefer this notation because this notation just inherits the notation from the joint random variables case. And as we already know, this is defined as expectation of 2 random variables product, X of T1 and X of T2. Sometimes, for example, if a random process is stationary to order 2 or higher, then what happens? Since this is a 2-dimensional integration with 2-dimensional density, in general, even after this 2-dimensional integration, this value is parameterized by T1 and T2. However, if this distribution is fixed, for example, stationary to order 2 or higher, then what happens? This becomes function only of time difference. So by using this notation, we may say this one, or we may even say something like this. Just a second. Yeah. Of course, this data is different from that data. And sometimes we use simply tau, then we may say this, or eventually we introduce very abusive notation. So the 2 functions have the same name, capital R sub XX, but the first one is a 2-variable function, and this one is a single variable function. But if the condition is satisfied, then they are the same. The Y-sense stationarity requires us to have constant mean path, and the autocorrelation function, a function of only time difference. Be careful, Y-sense stationarity does not imply stationarity to order 2 or higher, but the converse is true. One of the reasons why we use Y-sense stationarity is that even though stationarity to order 2 looks simple, it's not simple. How many two-dimensional joint distribution do we need to check? Uncountably infinite for continuous time random process and countably infinite for discrete time random processes. So it's actually very difficult. Got it? It's very difficult to estimate the joint distribution and verify whether that is only a function of time difference. So in practice, we prefer using Y-sense stationarity than the stationarity to order 2. Sometimes the more problematic case is that definitely the random process we are interested in does not have a zero mean, a constant mean. In that case, still we want to do something similar. In that case, what you do is this one. So suppose x of t, the random process, can be rewritten this way. So we have a mean path and the difference between x of t and the mean path. In that case, what do we have for y of t? Y of t is by definition a zero mean random process. Now, zero mean is a special case of constant mean. It would be great for our simple modeling that if y is Y-sense stationary. But in that case, zero mean Y-sense stationary. So in that case, what happens? The covariance function or correlation function of y is a function of time difference. That means covariance function, which means x of t minus mu sub x of t, has correlation function that is only a time difference. So covariance stationarity means that simply the covariance function is a function only of time difference. The mean function can be non-zero, a non-constant function. So we covered this part. And what about the independence between 2 random processes, 3 random processes, and random processes? They all are, the definition is all motivated by the Kolmogorov's theorem again. So what we do is that given any number of random processes, we take some samples, some arbitrary number of finite samples from these random processes, and we put them together to form a very long, possibly very long random vector. And that random vector has joint distribution that factors into each part of random vectors distribution. In that case, we have the independence. And what does that independence mean? Any event in terms of, for example, process x1, any event in terms of process x2, any number of events, as far as these events does not share these random processes, then they are independent. Ready? So that was the last part, and we are going to study joint stationarity and joint Y-sense stationarity. So we defined, given a single random process, we define the stationarity of the random process. What about stationarity of 2 random processes? You may say that, okay, I have 2 random processes, x of t and y of t, and x of t is stationary to order, for example, n, and y is stationary to order n. Then I may be able to say they are stationary together, but that's not true, because when we talked about stationarity, we sampled to get random vectors. And now, suppose we take samples from X at T1 through T sub n, and we sample Y at T tilde 1 through T tilde sub m. Okay, so let me use m and n. So m samples from X, n samples from Y. Then this random vector has a joint distribution, right? And stationarity means what? For any time shift, this joint distribution of this one does not change. What does that mean? Not just X and Y individually stationary, but this must be stationary too. So it's like we say that X of t and Y of t are jointly stationary to order, for example, some n. And here we choose n plus n equals or less than n. Okay, then in that case, this random vector must have the same distribution for any time origins choice, any choice of time origin. So any time shift does not change. Got it? So it's more than individual stationarity. Now, since this joint stationarity of some finite order or strict sense stationarity, joint stationarity is too complicated, again, we may use mean path and correlation function. So let's start from two random processes case. So we have X of t, Y sense stationary, and Y of t, Y sense stationary. What does that mean? Each random process has a constant mean. The means could be different. Each random process has its autocorrelation function, that is function only of time difference. Now, what would be one more condition or more than one conditions that may say that these are jointly Y sense stationary? So what you want to do is to what? Consider joint stationarity of order 2 and then apply expectation to have some useful constraint or condition. So what you do is that since if we choose two time samples because we talk about order 2 from X only, what do we have? Random processes X is, in this case, Y sense stationarity. If we choose two samples from Y, then you have Y sense stationarity of random process Y. Now, what if you choose one time instant and another time instant from Y, then you have what? X of T1 and Y of T2 random vector. And if you have two random variables, definitely you can define what? Cross correlation function. So expectation of X of T1 and Y of T2. Now, if joint stationary to order 2, then what happens? This R sub xy becomes what? A function of time difference. So joint stationarity means that not only individually Y sense stationary, but also cross correlation function is a function of time difference. Got it? So here we define the cross correlation function between two random processes, and here comes the condition. If it is a function of time difference, then we call what? These two random processes are jointly Y sense stationary. We don't need to consider two-dimensional function. We just need to consider a single parameter correlation autocorrelation and cross-correlation functions if we have joint Wiener stationarity. And you may say that, okay, good, but is there many random processes that are well categorized or classified as joint Wiener stationarity or Wiener stationarity? Of course not. Very restrictive. But very small number of random processes satisfy that. However, one of the most important random process is a Gaussian random process that is Wiener stationary. One of the most important. That is the topic of next section. So let's see, and let's define Gaussian random process. So consider a continuous time or discrete time random process x of t. Got it? It could be discrete time or it could be a continuous time. When do you want to call this random processes Gaussian? When? So again, we use what? We use the Kolmogov's extension theory. So we consider the first order distribution, second order, any nth order. And what do you have? In first order case, you have a random variable. In second order case, you have a random vector. In nth order case, you have a random vector of length n, and so on. Now, Gaussian. If I were you, I would say that, okay, first order distribution is Gaussian, second order Gaussian, nth order Gaussian, any finite order distribution must be Gaussian. In that case, I want to say it's a Gaussian random process. What else? What other name could it have, right? So Gaussian, 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 blah, blah, blah. Now, so that is good, but what would be the simplest definition in terms of distribution, joint distribution? So we again use the characteristic function, because the first order case, the characteristic function looks like what? Something like this, right? So the joint characteristic function is again a bell curve, the Gaussian bell curve that has j omega mean term that shifts this distribution in the complex domain. And we have negative omega square term that makes the curve smooth bell curve. Now, what about nth order case? You have now omega vector of length n. And what do you have? You have omega transpose and what? Mu sub x of, let me use just t vector. This is again a use of notation. What would that mean? You sample at the elements of this vector t. And so mu sub x of t underscore means a vector. And then what do you have? You have 1/2 times omega transpose. And here goes the covariance matrix of, again, abuse of notation. Let me just use this one. Just a second. T, yeah, x, t underscore omega. So this is again a random vector, even though it does not look like random vector, but let's just say that. So let me define like this, where mu sub x of t vector is mu sub expectation of x of t1, x of t2, x of tn, for example, and covariance xt, xt equals. Yeah, so covariance of x of t1 dot 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 x of tn. Ready? So yeah, this is the full characterization. Got it? Be careful. I didn't say that this mean vector must be constant. I never said that. I didn't say any other constraint on the covariance matrix. But here, it's very interesting that the full characterization of a Gaussian random vector is very interesting. See that? It only involves the samples from the mean path. It could be a function of time or constant function. Doesn't matter. However, it only requires information about the mean path and also only the covariance matrix of the sample. And let's take a more close look at this covariance function. What it is? By definition of the covariance matrix of a random vector, we have what? Covariance between x of t1 and x of t1 in the 1, 1 entry. And any ij's entry, we have x of ti, x of tj for any ij's entry. And what is that? What is that? We've already defined. This is simply the covariance function evaluated at ti and tj. So given a Gaussian random process, its full characterization can be done as far as you are given the mean path function and the two-dimensional. Be careful, two-dimensional covariance function. Got it? So as far as you are given these two functions, you have full characterization of a Gaussian random process, whether it is continuous time or discrete time. Of course, from these two information, you can also construct the autocorrelation function, because autocorrelation function evaluated at ti and tj is simply what? Cross covariance function evaluated at ti, tj plus, because this is centralized version, you mu mu sub x of ti times mu sub x of tj. Okay, so from these two functions, you can also derive the autocorrelation function, which is one of the most important and useful representative of a random process. Now, so far, we talked about a general Gaussian random process, right? In terms only of its distribution, any answer order joint distribution. And now, what if this process is stationary? Can you say something more? What if this process is Wiener stationary? What if this Gaussian process is covariance stationary? So let's take a look at the covariance stationary first. What do we have from this definition? So let's see this one. Covariance stationarity talks about the structure, property of this function. And in general, this function is a two-variable function, as I just told you. However, covariance stationarity means what? This matrix has each entry that is function of only time difference of two time instants, ti and tj, ti minus tj, right? So if your Gaussian random process is covariance stationary, how many information do you need to have a full characterization? Two functions. Now you have two one-dimensional functions. First one is the mean path, which is one-dimensional function of time. And the other is the autocovariance function, that is a function of time difference tau, only one parameter. Got it? Now, what if this Gaussian random process is y-sense stationary? Y-sense stationarity implies the constant mean by definition, and the covariance stationarity. We've already talked about covariance stationarity. Now, what do we have? We have full characterization if we are given two information. But first information is now what? A number, constant, because mean is a function. It's a constant function of time. So you don't need a function, you just need a number. So mean, the number, and the autocorrelation function, that is a single parameter function. Got it? Now, so we talked about Gaussianity and second order stationarity, right? But not strict sense, y-sense and covariance stationarity. What about strict sense stationarity? So the question is like this. When the Gaussian or Gaussian random process becomes strict sense stationary, or stationary to order 3, 4, 5, any n. So let's recall the definition. What do we have? We sample at a finite number of time instants and form a random vector, and its distribution does not change when we change the time difference. When do we have? Since this fully characterizes, if we add capital delta to time vector, which one does change? First, this mean vector may change if you change delta. But what does that mean? It does not change for any choice of delta. What does that mean? Also, what does that mean by invariance of that function by any choice of capital delta? You can easily see that this must be a constant function, and each entry of this covariance matrix must be function only of time. Then what is it? Y-sense stationarity. So from this definition of Gaussian random process, we can get immediately that when the process is Gaussian, Y-sense stationarity, if and only if strict sense stationarity. What does that mean? It's stationary to any order. Got it? So it's very interesting. In Gaussian case, that sloppy Y-sense stationarity is strict sense stationarity. Then the problem comes because many people, after they were taught about this equivalence between Y-sense stationarity and strict sense stationarity for Gaussian random process, they assume that all Gaussian random processes are Y-sense stationary and strict sense. It's not, okay? Because as you've seen here, suppose you have non-constant mean path, but still have covariance function, a function of time difference. In that case, it's not stationary, right? It's just covariance stationary, it's not stationary. And also, the mean path may linearly increasing, but still Gaussian, it can be. Got it? So be careful. Here are some examples from which you compute the correlation function and covariance function, and you do it yourself. It's not that difficult. Now, we learn one more important class of Gaussian random processes. So let me draw a Venn diagram again. Here we have the set of all Gaussian random processes. And again, an infinitesimally small subset claims that, hey, we are stationary random process, Gaussian random processes. But this means Y-sense stationarity equals strict sense stationarity. So that stationary to order 1, stationary to order 2, 3, 4, n are actually the same. Okay. Not exactly. So from second order. Okay. So still you may have something like stationary to order 1. Okay. So what people say is that if a Gaussian random process is stationary at least to order 2, got it? Which means that stationary to order 2, 3, 4, 5, 6, any n and strict sense station, they are the same. But still, you have stationarity to order 1, maybe outside this one. And this is quite exaggerated. We have another one. By the way, all these guys have what? Mu sub x of t equals constant. So we may say x bar for all t. And here goes non-zero mean, but very interesting Gaussian random processes. So let me a little bit modify this one. Okay, so yeah, I believe I'm correct. Yeah. So here goes the set of all Wiener processes, the set of all Wiener processes. So these Wiener random processes are Gaussian random processes, but very special. So let's see what are the definitions. There are typos here. I used n, but you must change it to w because we are using w to define. So suppose w is a Gaussian random process. So we have a subclass of Gaussian random process, right? So we have a Gaussian random process, but it's very, very interesting. Let's take a look at a sample path, okay? So this is W of t. It starts from 0. So at your choice of time origin, you also choose what? The spatial origin, okay? And you name it what? 0. So at time 0, W of t may be the location of, for example, a pollen in your Brownian motion, right? In x-axis, right? So you have some location of pollen. And then what happens? It may evolve as a function of t. So you have a sample path. Now, the definition is a little bit strange, but you've seen something similar to it already, because when you have seen Bernoulli random processes with parameter p, what did we need? We just needed IIDness and each one-dimensional PMF following by the Bernoulli random variable. And you could derive any nth order CDF or PMF of the random process. So that those two lines fully characterize the Bernoulli random process. Similarly, you've seen something similar to that. W of 0 equals 0. And then this looks very strange, but you choose T1 less than T2. So you choose at least the 2 points, right? They are different. Just you choose 2 points and name the bigger one T2. Got it? So T1 less than T2 implies, so here T1, T2, you have WT1, you have WT2, and you subtract to form a new random variable, right? You have 2 random variables, you subtract to have a new random variable, right? So if you change T1 and T2 pair, you have different random variable. Now, this random variable is what? Is Gaussian. So it follows Gaussian distribution with, here goes some interesting part, mean is 0. And what? The variance depends on the time difference. So you have T2 minus T1 times some constant. Here, alpha is positive if it is non-degenerate random process. For example, what if alpha equals 0? Variance is 0. What does that mean? It's 0, right? So it's constant for all 0. So let's remove that. So alpha is positive, and since we assumed T2 greater than T1, what? The variance is always non-negative, which makes sense, right? Now, why I claimed this is a Gaussian random process? Anybody? So in order to answer that, you have to show that this random process has any nth order distribution that is Gaussian. So let's consider the first order case. So you want to talk about the distribution of WT. How can you get it? Oh, good thing. If your choice of T1 is 0, then what do you have? This second term is 0. So intentionally, you choose T1 equals 0 and T2 equals T. Then what is this? This is simply W of T minus W of 0. Then by the second condition, you have Gaussianity, alpha T. Got it? So your random process sampled at time T2, if you want, okay, is always Gaussian. What if you want to choose T2 a negative value? In that case, what you do is that you choose T2 as 0 and T1 as a negative value. Then no problem. Got it? But usually, what we are interested in is usually T positive in this case, because we have said this is 0. Got it? But anyway. Now, let me ask you a question. So this is Gaussian in terms of the first order distribution. Is it first order? Is it stationary to order 1? And now let's take a look at this one. This is Gaussian, but its variance changes. What does that mean? It's not stationary to order 1. That's why I have this set here. It's never stationary to order 1 because its variance increases as you increase T a positive number. So its variance becomes larger and larger and larger and larger as you move far away from time origin T equals 0. Got it? Variance linearly increases. So it's never becomes the first order, stationary to order 1. But anyway, we've found the first order. What about second order case? What about second order distribution? Anybody? Anybody? So we need to sample at T1 and T2, right? And we want to derive the joint distribution. How can we derive it? Now, third order, fourth order, nth order. How can we do that? Anybody? So the idea is like this. Suppose you have T2. So you sample at T1 and T2 is greater than T1. You form this random vector to talk about the second order distribution. Now, what would be the trick? What would be the trick? You have these two intervals, right? And actually, I missed one more something to talk about that. Here, this interval, two intervals, they have no overlapping, have independence. And you want to say independent somethings. And they say that independent increments. And here, any Ti and Tj, you have Wti minus Wtj. So given two time instants, this W of Ti minus W of Tj is called the increment corresponding to these two pairs. So let me see. Increments. Yeah. So independent increments means that as far as two intervals does not have intersection, or it may have intersection but zero something, but we prefer no intersection. Okay, and yeah, it's how to say that the endpoints, the right end and left end of two intervals may coincide, no problem. But anyway, so we need third condition to talk about higher than 2 distribution. Now, what is this? W2 and W1 has some relation like this. WT1 minus WT2, sorry, WT2 minus WT1, and WT1 minus W0. And this can be linearly transformed to generate the left-hand side. How? 1, 1, 0, 1. Am I right? So if you add these two increments, what do you have? You have W of T2. Am I right? See that? You add up this and this cancels, and you have W of T2 minus W of 0, which is W of T2. And the second, you have this one, which is W of T1. And the third condition, independent increments, implies what? This random vector is what? Independent and what? Gaussian. And we already know that any linear transformation, any affine transformation of a Gaussian random vector is Gaussian. What does that mean? Second order distribution is Gaussian. Got it? Now, what about third? We do the same thing. So here we have WT3, WT1, sorry, T2, T1. And what do you want to do? You want to have 3 disjoint intervals. So W of T3 minus W of T2, W of T2 minus W of T1, W of T1 minus W of 0. And what? You add them up to have W of T3. You add them up, So what do you have? The upper triangular matrices with all 1 entries gives you what? Gaussianity of any nth order joint distribution. Right? So we've done. It's Gaussian. Got it? But it's not even stationary to order 1. It's not because its mean is non-constant. Its mean is constant. Mean path is 0 for all t. How can you show that? Because we've already have derived the W of t has what? 0 mean for all t. E to the W of t is 0 for all t. So the requirement for Y-sense stationarities, the first requirement, constant mean, is satisfied. However, its autocorrelation function has strange thing because of this linear increase in the variance. Got it? So never forget this. So here you have the set of all Wiener processes. This Wiener process is also called the Brownian motion process, or here we all just simply removed random process, just process. Okay, it's not some procedure, it's a random process. Okay, Brownian motion random process, Wiener random process. They are all very special case of Gaussian random processes. And here we have restricted to our discussion to continuous time, but actually you can have exact counterpart in discrete time random processes. Now, what about joint Gaussianity? When do you want to say two random processes are jointly Gaussian? Now it's simple, very simple from the Kolmorov's theorem. Each individual random process is Gaussian, and any random vector consisting of sub-random vectors, sub-random vector from X, sub-random vector from Y. And if you have some 100 number of Gaussian random processes, you take what? At most 100 sub-random vectors and put them together. And as far as this random vector is Gaussian, they are jointly Gaussian. What about jointly Gaussian and stationary? You know how to expand your definition. Got it? So we are done with Gaussian random processes. Now we want to move to this exciting part of Poisson random process. One of the reasons why it's very exciting is that it's very complicated. Okay, it's very complicated. It's confusing a lot, but let's overcome the confusion together. So let me show you first a sample path, because this clarifies a lot. Okay, so let's take a look at this sample path. What do you see? What do you see? Actually, some people prefer to define a Poisson process as a process defined on time t non-negative, as I just told you about the Wiener process. Okay, but it's not exactly necessary. You just need to move in the Wiener process case. You just choose t0 and the location s0. Then you are done. But in this Poisson case, it's a little bit complicated to do that, because as you see, the sample path is what? Piecewise constant. So even though you say that time t something as of course, if you fix time t, then your value is automatically defined, but not the converse is true. So your value first, and you have ambiguity in choosing the origin. But anyway, so this increases, the sample path increases only a single step. So as you see that, it's piecewise constant, but it increases by a unit amount. And let's call the unit amount as 1. Got it? So it only increases. So all the sample path increases. It never decreases. And what else? Here, it's a continuous time function. So sample path is a continuous time function. What does that mean? The random process is a continuous time random process. So we call usually the Poisson process as n of t with parentheses. What does that mean? N looks like a number, right? So a Poisson process n of t. First, it's a continuous time random process. Two, increasing sample path with unit amount. What else? Of course, as you see here, we intentionally choose n0 equals 0. Now, you may define actually something similar to this one in a discrete time case. Just the time is now an integer. And at each time, either your value of the random process increases or just stays, right? So you may have something like sample paths that look like something like this. At 0 equals 0, at 1, it could be 0 or 1. Let's say in some case 0. At time 2, it could be 0 or 1. Let's say it's now 1. At time 3, it's 0, 4, 0, 4. At 5, 1, something like that. Ready? However, when we talk about a Poisson random process, we don't think about such a discrete time random process. We consider a continuous time random process. Now, the most confusing is this one. Here, you say that instead of t, you say s. One of the reasons why is this is that you want to define discrete time random processes from this Poisson continuous time Poisson random process. How do they do that? It's like this. Whenever you have jump, right? See that here? At time s1, you have the value change. So you have something like this, right? At some time s2, you have a jump in your value, right? Now, from 0, you may number this time instance. Then what? You may say that, okay, I may construct, this is very confusing but important thing. From a Poisson random process, you may induce or derive new random process S sub n. Here, n is a natural number. What S1 means? Time instant at which your value jumps from 0 to 1. What is S2? So suppose this is 1.5 and this is 3.2 or something like that. Then you have some discrete time random process that shows 1.5, 3.2, 3.5, 5.9, something. That increases, right? That always increases. But here, since we said that there is no double jump, triple jump, what do we have? N of Sn. This is very complicated, but remember that S means what? S means time instant. So it can be put into the argument of this random process. What would it be? equals n, right? Because this is what? The nth time instant where you have a single increment. So this is n for all n integers. Okay. But anyway, you have this interesting thing, and also Sn plus 1 is greater than Sn for all n. Now, here you want to say, what about just to say that S0 equals 0? But careful. Some people, just when they think about positive time, then they say that S sub 0 equals 0. But if it was defined from a random process from negative infinity to positive infinity, and you choose some time origin, then it may have S0 here. Okay, so be careful. But anyway, so this is what you have. What does this mean? You have only one increment. And that is sometimes used to model the arrival of customers at a store, for example. And of course, there are cases two customers arrive at the same time, but infinitesimally small difference you may introduce anyway in a continuous time. So you may just say that, okay, in order to define a Poisson random process, let me just assume that single arrival at a time, something like that. By the way, random processes, class of random processes that increases by single unit is called the counting process. So let me draw a Venn diagram again. So here we have the set of all counting processes. And here we have discrete time and continuous time counting processes, right? As I told you. And the Poisson random process is here. Got it? So it's a continuous time random process. However, even though this is a continuous time random process, counting random process, you can derive a discrete time random process that perfectly has all the information about the realization of sample path of the Gaussian, the Poisson process. That is what? We want to name this one. And what is this? This is called an arrival time process. Because if we assume that this is number of customers arrived from some time reference 0, this is called what? An arrival, of course, time random process. So an arrival process has something like this. T of S is greater than 0 for all n in a natural number, and Sn plus 1 is greater than Sn for all natural number n, and what? It is related to a counting process in this way. The counting process n evaluated at Sn equals n. Okay, so a counting process has its what? Its twin separated in their childhood in a discrete time world, okay, and named as arrival process. And Poisson process's arrival time process is called Poisson arrival process. Got it? So given a Poisson process, n of t is equivalent to a Poisson arrival process. However, actually, this is what? A Poisson counting process. Because its value, the random variable, means number of counts of arrival of customs. Okay, so this counts, but this is what? Arrival time process. They are different processes having the same information. This is discrete process, discrete time process if you want. This is continuous time random process. So even though it's very confusing, I believe you are not that confused as I was in 30 years ago. So here goes some highlights. So we have a big subclass of counting processes. And a counting process could be discrete time or continuous time process. An arrival process can be derived from a counting process, right? Even from a discrete time counting process, you can define discrete time arrival process. No problem, right? There is a third one, and it's also confusing. And this is also an equivalent one. It's an inter-arrival time random process. Inter-arrival time random process. And time and random, these two words are just dropped in many times. What is this one? This is what? This is the time difference process derived from the arrival time process. So it's like this. You define x1 as s1 minus 0, x2 as s2 minus s1, So xn equals Sn minus Sn minus 1 for all n greater than or equal to 2, something like that. Got it? Then what is it? It's a discrete time random process, right? It's a discrete time random process. And what property does it have? It is always greater than 0 if your original counting process is a continuous time counting process. It is always greater than or equal to 1, right? Because there is no, if there is no double arrival for discrete time counting process. So here goes the complicated thing. So you may define a counting process. Then you can define arrival time instance. From that, you may equivalently define a discrete time random process. That is called the arrival time random process, simply arrival process. And from arrival time random process, you may define what? Inter-arrival time random process. So you have the relation between each of two. Now, let's go back to our Poisson process. So given a Poisson process, in our case, a continuous time counting process, very special. Why is it called a Poisson random process? Why? Why is it called a Poisson process? It's highly likely that this n of t is a Poisson random variable, but that's nonsense because a Poisson random variable has what? Arbitrarily large number in general, right? Even though its probability may be very small. So it seems that something's wrong with this definition. What is wrong? See that at each time, it's finite, right? But that is only true from this sample path. You don't know how many customers arrive at a specific time. So it's still okay to have Poisson distribution. And actually, that is true. So the first is that you have n0 equals 0, and you have n at some time t. Of course, in this case, usually we assume t positive. This is what? This is a Poisson random variable with parameter what? That is very important. Here, when you define a Poisson random variable, you need a single parameter. And that single parameter is what? Something like this. So let's say that parameter is alpha. Then what? Probability mass function over Poisson random variable x is what? You have n factorial and e to the negative something, right? And what? And what do we have? Something to the n. What is that? And if this number, let's say that this is alpha, right? Then, as you remember, this equals 1 because what? This is simply e to the negative alpha times, 1, 0 factorial, 1 factorial, 2 factorial. So this becomes e to the alpha, right? Now, what if alpha increases? What if alpha decreases? What does that mean? If alpha increases, then what? But can it be larger than 1? What happens? It could be larger than 1 because this anyway makes every terms less than 1 and sum up to 1, right? What happens? And this alpha must be fixed for Poisson random process or not. And that hint is already given from our Brownian motion random process. It seems that if t increases, right? If you have a counting process, you may have larger and large probability for a bigger number. So somehow you have to have time-dependent parameter alpha for this random process to be a Poisson, to have a Poisson distribution and also to be a counting process. So here goes the definition. Where it is? Where it is? Where it is? Just a second. Okay. Yeah. So yeah, distribution is like this. So probability mass function.
Joe, it is time to wrap up.
Probability mass function at time t equals what? As I told you, 1 over n factorial e to the negative, here goes lambda t, and lambda t raised to the power of n. What is that? T is time instant. So it's kind of this parameter, formerly alpha, linearly increases. And now, as it increases, the probability of higher, greater number is kind of increasing. Okay? In that reason, it's not full characterization yet, but one of the reasons why this counting process is called Poisson is that its first order probability mass function is what? Is following the Poisson distribution. Got it? Okay, we couldn't finish this part today, so let's continue next week.